All right, here we are in chapter 6, looking at valence bond theory and talking about hybridization. So to make sure that you're ready to do the homework here on chapter 6, let's talk about the bonding scheme for some molecules. Okay, if we look here at bromine, bromine has 5 electron groups around it. That means the bromine is sp3d1 hybridized. Okay? The fluorines, they're using a p orbital because they have 1 unpaired electron. They're not between 2 other atoms, so we don't talk about them hybridizing. Only the atom in the middle. So each one of these bromine-fluorine bonds is made by overlapping an sp3d hybrid orbital from the bromine with a p hybrid orbital from the fluorine. And they're all the same. Okay? If we come and we look at CH3COH, this carbon has 4 electron groups around it, so it's sp3 hybridized, and it's overlapping with a 1s orbital from hydrogen. So it's a 1s sp3 overlap. With this carbon has 3 electron groups with it, so it's sp2. So I have an sp3 overlapping with an sp2. Okay? Here I have a sigma and a pi bond, an sp3 overlapping with a p, and then a p from here overlapping with a p for the second bond. And here, sp2 overlapping with an s. Now, your book has some really pretty pictures. I wouldn't expect you to be able to draw them. Okay? So they're showing the sp3 hybrid orbitals and the p's. They're showing sp3d1s, sp3. Okay? There's the sp2, and there's the hybrid orbital, and it's labeled them. Okay? Just like we did. sp3 overlapping with an s, a p overlapping with a p in the pi bond, and sp2 overlapping with a p in the sigma bond, that first bond. So when you get into homework, you're going to see some of that, and I want you to be ready and able to handle it. All right, now, chapter 6 is a tale of 2 parts. The other part of chapter 6 that we're trying to deal with is a second bonding theory. Okay? Valence bond theory is really good at explaining the shapes of molecules. But there were some molecules whose electric and magnetic characteristics could not be explained by the combination of Lewis dot structure, valence bond theory, VSEPR. Okay? And the classic example of this is oxygen. So if we look at an oxygen molecule, O2, there are 2 oxygens, of course, at 6 electrons apiece. That means we have 12 electrons. So oxygen and oxygen side by side connect up with a single bond, 2, 4, 6, 8, 10, 12. So 2, 4, 6, 8. Excuse me, I went too far. So 2 there, minus 2, 10, 2, 4, 6, 8, 10. So I'm going to have to make a double bond to fix this. I'm going to take a lone pair of electrons here, fold it in, and make a double bond. Okay? So when we look at this, we see a double bonded oxygen, and we see 4 lone pairs. Looking at this as a molecule, there are no unpaired electrons. This molecule should be diamagnetic, which means it won't be attracted to an external magnetic field. Okay? Paramagnetic atoms, ions, and molecules are attracted to a magnetic field. Experimentally, though, what they discovered is that oxygen is actually attracted to a magnetic field. Now, I don't have any liquid oxygen to play with, but I do have pretty pictures. Okay? What you're seeing here is liquid oxygen being poured between the poles of a curved magnet. So you got a North Pole and South Pole. What's important here, and what people wondering what was going on, is the fact that the liquid oxygen gets trapped between the two poles. Now that tells us that it has a magnetic characteristic. If it was diamagnetic, it would pour straight through and we'd see nothing in here. Okay? It's working for me today. Clear we need another approach to be able to explain the magnetic and electronic properties of the molecules. So, what we're going to do is we're going to go back and we're going to try to expand something that was used earlier. When we first started looking at the energy of electrons, we used the Schrodinger equation for the atom of interest. So, we should be able to do the same thing with molecules and assume that when atoms bond, okay, they create a new set of orbitals that are unique to that molecule. And this is called a molecular orbital, and we're getting ready to talk about molecular orbital theory. So when atoms bond, okay, according to molecular orbital theory, nobody keeps anything that was theirs originally. Everybody gives up their atomic orbitals, and they make a new set of molecular orbitals that are unique to that molecule. Now, molecular orbital theory and the math of it is very complicated. So we're going to stick to very simple cases. Okay, we're going to look at combining two atoms together. We're going to look at only diatomic molecules. And we're really only going to look at diatomic molecules where we put two identical atoms together. I'll mention here at the end some stuff about maybe a nitrogen and an oxygen, but very limited, okay? Now, when we're thinking about the Schrodinger equation and building these new molecular orbitals, I want you to remember that Schrodinger was concentrating in on the energy of the atom, the electrons in the atom, and he was concentrating in on the wave behavior. So what we're doing here, when we're looking at molecular orbital theory, is we're looking at adding two wave patterns from two different atoms together to create a new wave pattern. Now, when we add waves together, and that's not being real, come on, you were working for me a minute ago. When we are adding waves together, we can add waves together constructively, or we can add waves together destructively. There's always two possibilities. Now let me show you very simply constructive and destructive, and then we're going to look at it when we talk about the atomic orbitals. So if I have this wave and this wave, we talk about them being in sync with each other. They're doing the same thing at the same time. When they add together, I get a wave that's much bigger. This is constructive. If they're doing the opposites, okay, this is destructive and they cancel out. Whenever we add orbitals together from two different atoms, we're going to get a constructive possibility and a destructive possibility. So when I add two things together, I always get a constructive, a destructive. Two orbitals go in, two new orbitals go out. So two atomic orbitals go in, two molecular orbitals come out of that addition. So we're going to start first by looking at adding 1s with 1s. Okay, now the book does prettier pictures than I can draw, so we're going to use the book's pictures. So if I mix a 1s together with a 1s, and they add together constructively, then the region where they overlap, okay, I'm going to get reinforcement. They're going to be doing the same thing at the same time, and we get this nice kind of capsule shape molecular bonding orbital. Okay? It's called a bonding orbital because there is shared electron density between the two nuclei. No, don't want to. Okay. Haha, now it's moving again. If they add together destructively, okay, so that you can think about it like a subtraction, when they add together destructively, they're doing opposite things where they overlap. That's why you're getting a red and a blue here, because they were doing opposites. And you get a node in the middle. Remember, a node is a place where the electron density or the waves add together to give you a 0. This is called an anti-bonding molecular orbital. Anti-bonding is always higher in energy than bonding. Remember, electrons want to go into lowest energy position first. So when we overlap two atoms to bond, and we create molecular orbitals of bonding type and anti-bonding type, bonding is always lower in energy than anti-bonding. Okay? So this destructive addition ends up with higher energy. And it's always going to have an asterisk. Now, notice that the new molecular orbitals are along the line that connect the two nuclei. These S blendings. So they're called sigma molecular orbitals. And they get a subscript of, in this case, 1s, because they were made for blending together, a 1s orbital from atom 1 and a 1s orbital for atom 2. Now, we're going to start off, come on. Half the time it works, half the time it doesn't. Now, here we have two hydrogen atoms, pre-bonding. Okay, they have one electron in a 1s orbital. Now it's showing them with opposite spins because when they end up in the bond, they're going to have opposite spins. Okay, a 1s orbital blends together with a 1s orbital to create a sigma 1s bonding and a sigma 1s anti-bonding. Now, to make the molecule, the electrons that were originally in the atomic orbitals are moved into the molecular orbital. So the one electron from there, the one electron from there. We have two electrons in the molecular bonding orbital. Okay? Now, as long as you have more electrons in bonding orbitals than anti-bonding orbitals, the molecule can exist. Okay? And we check this by calculating a bond order. Now let's talk about what bond order is. Bond order is calculated by taking number of electrons in a bonding molecular orbital, subtracting the number of electrons in an anti-bonding molecular orbital, and dividing by 2. The bond order for an H2 molecule then is 2 minus 0 divided by 2. That gives us a bond order of 1. As long as the bond order is greater than 0, okay, positive value, then the molecule can exist. Okay, finally. Okay, now let's look at helium. Helium has 2 electrons. So here's the atomic orbital and helium atom, right side, helium atom left side. If we make molecular orbitals, we have a sigma 1s and sigma 1s star. Okay? So if we start doing that, then we've got to move 2 electrons in from there, 2 electrons in from here, 1, 2, 3, 4. Okay? These are moved into here. And we got to calculate the bond order. Well, we've got 2 in a bonding, 2 in anti-bonding. 2 minus 2 is 0. 0 divided by 2 is 0. The bond order for a helium He2 molecule is 0. So molecular orbital theory says a helium molecule can't exist. Now, let me see if we want to do practice problem 6.4. Okay. It says apply molecular orbital theory and predict the bond order for a H2 plus 1. Well, let's try the other one. Let's try an H2 minus 1. Okay, let's come over here. So it wants us to calculate the bond order of an H2 minus 1. Now, that means that one of the hydrogen atoms has been given an extra electron. So I'm going to have a hydrogen 1 minus and a hydrogen atom. So the hydrogen 1 minus is going to have 2 electrons in the 1s. The regular hydrogen has 1 electron in the 1s. So I'm going to have, I blend together a 1s and 1s. I'm going to have a sigma 1s bonding and a sigma 1s anti-bonding. That's what the asterisk is for. And I've got 3 electrons to move in. So 1, 2, 3. Okay? The bond order here is going to be 2 minus 1 divided by 2. We get a bond order of 1/2. That means that this molecule can exist. Okay? So a bond order of 1/2. Now, let's move on to lithium. And think about lithium because it's in the second period. Lithium's electron configuration is 1s2, 2s1. So lithium atom number 1, lithium atom number 2. If I do box diagrams, 1s has 2, 2s has 1. 1s has 2 over here. 2s has 1. Now, we're going to blend together 1s and 1s and 2s and 2s. One s is going to blend together with 1s to give us a sigma 1s bonding. And then I'm going to sigma 1s anti-bonding. And then I'm going to get a sigma 2s bonding and a sigma 2s anti-bonding. Okay? Now, I'm going to take an electron from here and an electron from over here. And then an electron from here, and an electron from here. So there's the 4 electrons that were in the 1s between the 2 atoms. And then I got 1 here and 1 here. Now, I want to show something to you. I want you to notice something. I'm going to draw a line right here. If you look down here in the first shell, okay, notice I have as many electrons in bonding as in antibonding. You know, in the past, electrons that were not in the outermost shell we called core electrons. We're going to do the same thing here. These are core electrons. We're always going to have as many in bonding as we do in antibonding. So core electrons do not affect whether the molecule holds together or not. So we're going to ignore them. Okay? They're there, they're in molecular orbitals, but they're not going to determine if the molecule can exist or not. Just like in Lewis dot valence bond, it's the valence electrons that are important in determining if the molecule holds together or flies or can't exist. So if I look at just the valence, what I get for my bond order is 2 minus 0 divided by 2, a bond order of 1. So a lithium molecule can exist. Okay? It's a dilithium. So let's move on and try beryllium. Now, from here on out, we're only going to draw the molecular orbitals for the valence of the atom because the valence is the part that's important. Now, if we look at beryllium, its electron configuration is 1s2, 2s2. Okay? I'm going to concentrate in just on the valence. So I have 2s, and it's got 2 electrons. And just because I can, we get a sigma 2s bonding, a sigma 2s antibonding. Okay, notice the bonding is always lower in energy than the original atomic orbitals. The antibonding is higher. And so I'm going to get a situation that looks like this. Okay? We move 2 electrons, 1 from each of the atoms into the sigma bonding, 2 electrons, 1 from each of the atom in the antibonding. So the bond order is going to be 2 minus 0 divided, 2 minus 2 divided by 2, which gives me a big fat 0. Okay? So there's beryllium and its bond order. So a beryllium molecule does not exist. Okay? Now I've got the images from the book embedded in the notes, and of course they're prettier than mine. Okay, let me show you. But it's a little easier for me to talk through when I'm drawing. So there's what the image looks like from the book. And I like to color code things. if we move on to boron, the next element over, electron configuration 1s2, 2s2, 2p1. We now have p orbitals that we need to look at combining. And let's think about p orbitals here for a second, okay? Again, let me draw. The p orbitals are that dumbbell shape, okay? So let's think about having two atoms sitting side by side. Now, they're going to have p orbitals along the x-axis. They're coming at each other end to end. Okay? We got p orbitals sitting along the y-axis. They're kind of sitting side by side. The z-axis is the same way. They're sitting side by side. So when we're looking at adding p orbitals together, the px, the p's along the x-axis, are going to add together differently than the p's along the y and the z-axis. Okay? So keep that in mind as we start looking at combining p orbitals. All right. So let's go back to the pretty pictures. Now, here's a px and a px. Okay, they're coming at each other end to end. Since they're coming at each other end to end, we're going to get, and I'm sorry, but that should be a sigma, not an S, okay? But we should get sigma type additions. Sigma additions are always along that barrel that connects the two nuclei. So it's along the line that connects the nuclei. We can get a bonding addition where those two pieces overlap, they're doing the same thing at the same time, and they get, a nice fat center section, okay? And we can get an anti-bonding addition. The anti-bonding addition has a dead space because they're doing opposites. That's what they're doing with the color coding here of blue and red. They're doing opposites. Blue and blue, they're doing the same thing. So we get a sigma 2p bonding and a sigma 2p anti-bonding. All right? Scroll down some more. So we get constructive and destructive additions. Now let's look at combining a PZ with a PZ. Told you earlier, they're coming at each other side by side. Okay? If they add together constructively side by side, we get an electron density here and here. This loops above and below the plane that contains the nuclei. So that's a pi addition. Just like we use pi in valence bond theory to be that bond that was side-by-side p's, here again, side-by-side p's. We get a pi molecular orbital bonding version. And if they are doing the opposites, so they add together destructively, we get a dead zone. I always thought about this as looking like halves of a butterfly. Okay? But anti-bonding, bonding. The addition of side-to-side y orbitals is just like adding side-to-side z orbitals. So when I add p orbitals with p orbitals, px and px give us a sigma 2p bonding, a sigma 2p anti-bonding. When we add together pz and pz, we get a pi 2p bonding and a pi 2p anti-bonding. And when we add together PY and PY, we get a pi 2p bonding and a pi 2p anti-bonding. Okay? So remember, if we're using sigma in valence bond theory or we're using sigma in molecular orbital theory, we're talking about an orbital or a combination that's along the line that connects the two nuclei. If we are using pi, we're talking about something going above and below the plane that contains the two nuclei. Okay? Now there's the picture of the PY and the PY. That side by side again, just kind of reinforcing the orientation. Okay. So, in a perfect world, okay, we would see the molecular orbital energies in the second shell stack like this. The sigma, well, I'm going to have to roll this up a little bit because I'm just showing you the P's there. Yeah. Shrink this down just a little bit so we can get it all in on the screen. In a perfect world, okay, here's how the energies would stack in the second shell. Sigma 2s bonding would be lowest. Sigma 2s anti-bonding is next. Sigma 2p bonding. Then the pi 2p bondings, two of them. Then the sigma 2p the pi 2p anti-bondings. And last, sigma 2p anti-bonding. Okay? This is a perfect world. Not all atoms go by the perfect world. This is a situation where there's no mixing between the s and the p atomic orbitals when it comes to making molecular orbitals. There's no orbital-orbital cross influence. And this is what we see for O2, F2, and Ne2. But for boron B2, carbon C2, and nitrogen N2, there is a mixing effect. There are influences between the s and the p orbitals that affect the energy stacking. Okay? And instead of the sigma 2p bonding being the lowest in energy, the pi 2p bondings are. I have a love-hate relationship with this screen. Okay? So, the energies are slightly different for boron and carbon and nitrogen than oxygen, fluorine, and neon. Okay? Now, here are just the molecular orbital box diagrams for B2, C2, N2, O2, F2, Ne2. Okay? Now guys, keep this in mind. You're going to hit some homework, and being able to look back at this is going to be important for you. Okay, so notice that in B2 we have 2 electrons in sigma 2s, 2 in sigma 2s anti-bonding, and then 2 electrons in pi 2p bonding. So 1, 2, 3, 4 electrons in bonding, 2 in anti-bonding. 4 minus 2 is 2. 2 divided by 2 gives us a bond order of 1. And it's going to be paramagnetic because it has 2 unpaired electrons. Okay, carbon has 1, 2, 3, 4, 5, 6 in bonding, 2 in anti-bonding. 6 minus 2 is 4. 4 divided by 2 is 2. Bond order of 2. A carbon molecule can exist and it's diamagnetic. Nitrogen, go through the same thing. We're going to get a bond order of 3 and it's diamagnetic. When we come over to oxygen, this is where we get no mixing between the molecular orbitals. So I have sigma 2s, sigma 2s antibonding, sigma 2p bonding, pi 2p bondings, pi 2p antibonding, sigma 2p antibonding. So I have 1, 2, 3, 4, 5, 6, 8 in bonding. And I have 1, 2, 3, 4 in antibonding. 8 minus 4 is 4. 4 divided by 2 is a bond order of 2, like the two lines we draw in a Lewis dot structure. But notice now I have 2 unpaired electrons. Oxygen is paramagnetic. Okay? You can look at fluorine, you can look at neon. Now you can use these guys as a poster children for elements in their family. So sulfur's molecular orbital box diagram should look like oxygen. Chlorine's box diagram, molecular orbital box diagram, should look like fluorine. Silicon's box diagram should look like carbon. So you can use these guys as kind of templates for the other members of their family. Now, if you look at practice problem 6.5, it says draw the molecular orbital diagram and determine the bond order for nitrogen plus 1. Guys, I can use this. Nitrogen N2 plus 1 just means a nitrogen molecule with 1 electron missing. So you always take one out of the highest energy level. So I'd remove that electron. So now I have 1, 2, 3, 4, 5, 6, 7 in bonding, 2 in anti-bonding because I took 1 out. So 7 minus 2 is 5. 5 divided by 2 is 2.5. So instead of having a bond order of 3, it now has a bond order of 2.5. It still exists. Okay? All right, now, if you were to look at I'm not going to give you anything like practice problem 6.6 that has a diatomic molecule where the 2 atoms are not identical. Look at example 6.6. It's on page 277 in your book. Also, I want you to notice on page 276, let me switch over to the document camera. Okay, what we have here is a molecular orbital diagram for nitrogen monoxide, the No molecule. Okay, and you can see how the energies of an s orbital in nitrogen and oxygen are different from each other. So the s orbitals are at different energies, the p orbitals at different energies. And there's what the mixing looks like. No, I wouldn't expect you to be able to draw that on your own. And just like if I had 2 nitrogens or 2 oxygens, I migrate everything in from the atomic orbitals into the molecular orbitals. Okay? And you can calculate a bond order here. So there's 1, 2, 3, 4, 5, 6, 7, 8. I have 8 minus 3, so I'm going to get a bond order of 2.5. Okay? If I scroll this down, there's a hydrogen and a fluorine. You're blending together a 1s with a 2 with the 2 p's from fluorine. It gets wonky. I'm not going to expect you to be able to draw that on your own. Now, remember earlier when we talked about the valence bond model and we talked about Lewis structures, okay, and that there were 2 ways to draw something like ozone. And this is a valence bond representation of one of those 2 resonance structures. Okay? In molecular orbital theory, since all of the atoms are sharing all the electrons in common molecular orbitals, we get a smearing of bonds. The pi bond is delocalized. Okay? So if you go in here and you look at the bond length and the bond strength for each of these oxygen-oxygen bonds to the central oxygen, they're the same length, they're the same strength, and they measure in at about a bond and a half. Okay? So it's kind of cool. If we look down here at benzene, C6H6, there are two different resonance structures. Okay? The only difference between these two is where we place the double bonds and where we place the single bonds. But when you go and you look at benzene, all of those carbon-carbon bonds are the same length and the same strength. And again, molecular orbital theory explains this very nicely. We can talk about the electron density from those double bonds being smeared across the whole molecule. So it's very symmetric. It has 6 identical carbon-carbon bonds. So having that smear is the best way to represent things. And it doesn't require having 2 different drawings, okay? It explains the molecule that looks somewhere in between. And this, guys, is the end of chapter 6. Okay? And, well, this is just the end of chapter 6. I know this chapter can be a little bit hard because it's very conceptual. Just take your time, read the book, and just be careful.